Okay, please join me in welcoming Shibl. Shibl Mourad is Director of Research and Engineering at Google DeepMind. He leads engineering teams focused on improving AI capability for Gemini and other Google models in areas such as reasoning, code, mathematics, and health. Shibl is passionate about combining best-in-class engineering practices with machine learning research to advance frontier of AI and use it to build better world. He holds a master's in artificial intelligence and BEng, Bachelor of Engineering and Computer Science from Queen Mary's College, University of London. This is not in his bio, but he also very passionate about building startups and building practical applications. So if you also want to ask about these things, he's my favorite person to talk to and debate all the matter of lives. So please join me in welcoming Shibl. Thank you so much.
Good morning, everyone, and thank you for joining me here on the fourth day. It has been long so far, and I hope you are enjoying it. Thank you, Sami, and you are one of my favorite people to talk to as well about many, many topics. And I want to thank as well the whole organizing team, including Sami, Maria, Safa, Yazan, Nasim, and everyone else who I'm sure there's many people I forgot. Yeah, actually. I want to thank as well KAUST. This place is so amazing. I'm so jealous of what you have here. I would have loved to be here when I was studying. How many people, can you raise hands if you are from KAUST? Thank you, KAUST. Very good. And obviously, I want to thank every one of you. I think I spoke to many of you. I learned a lot from these interactions. And I'm so excited about the talent we have in the Middle East. And I hope this conference, I think you can attend the talks and so on. You can talk to mentors. But the most important thing to do is actually to talk to each other because these collaborations that you are building here can end up with a lifetimes of results. And hopefully, together, we can build a Middle East that's based more on science and collaboration and these kind of things so that us and our children can have a better life in the future. All right, so I'm going to talk about building a science assistant. My talk has two objectives. The first objective is to explain to you a paper that we have done, but as well I want to give you a bit of how things are done so that you can model it for your own research, and when you see things published, you understand, okay, what happened behind the scenes. All right, so next slide, please. Do I click? All right, I will do the next slide. Okay, so in September, this was a blog post on Google website claiming that we're accelerating science with AI-powered empirical software. And the name is very interesting. So what does empirical mean? It means that this is software that can conduct experiments. So typically, when we use Gemini or other tools, even deep thinking tools and so on, they're thinking on their own. So they're in their own mind. Sometimes they do retrieval. They do these minor things. But here, the idea is that this thinking loop actually involves running experiments. Obviously, not obviously, but sadly, the experiments are computer experiments. Hopefully, in the future, we can let robots run actual experiments. But these are experiments run on the computer. OK, so this paper was, this blog post was published with a paper connected to it. And if we go to the paper, we see all of these names on the paper. OK, so how did all these people get together to do that thing, right? And majority of these people worked for a year and a half to generate that result. These people include computer scientists, but include as well people who understand biology, people who understand neuroscience, people who understand medicine, and people who understand mathematics. They all collaborated together to get that result. OK, so my objective is to show you how the dish is cooked. So my first question to you is, do you know what this dish is? Raise your hand if you know. Nobody knows. Sami knows. What is it? Fatet, yes, exactly. It's, or more specifically, in Syria, we call it fatet makdous. Now, this is my favorite dish. So I highly recommend you look it up. You learn how to cook it. It's amazing. OK, so let's go back to the Fateh Magdous. Okay, so let's go back to day one. So what was day one is a bunch of us are sitting together and saying, LLMs are amazing. What are the things that we don't know if they can do or they cannot do? So lots of brainstorming, lots of coffee, discussions, and we say, okay, obviously the hardest cognitive task we have is the scientific task. So can LLMs do what a scientist does? And this is from us because we are from a computer science perspective. When we started, our objective was not applicative. It was more to see the reasoning of the LLM, how far they can go, and what kind of algorithm we need to add to them so they can go even further than where they go today. Okay, so that was the initial thought. And then after that initial thought comes the second thought is, okay, how do we eval? And okay, now here's the second question to the audience. Do you know what this is, this picture? Okay, raise your hands, people who know. Okay, now keep your hands up. Okay, do you know the name of at least one actor? If not, bring your hand down. Do you know the name of two actors? Keep hands up. Do you know the name of three actors? Okay, we have three people who know the names of three actors. I'm assuming what you actually are trustworthy. So I'm going to put there's three gifts here that you can pick up. You can come and take them. Please come and take your gifts. The people who knew the names, I think there's two people in the back. Yeah, you have gifts here. Come over. Or Nassim is, okay. All right, so okay, the very important question is how do we evaluate? How do we evaluate? Because evaluation is one of the core things if you are doing machine learning research. If you don't have a good eval, basically you are going to waste a lot of time. And as well, it's not only having good eval, it's having consensus that the team has consensus that this is the thing that we are going to evaluate our results on. This makes it very metric-driven research. So when people come up with ideas, they're all evaluating their ideas on the same thing. And this allows you to have a small team working on a project, but you can span to 20, 30, 40 people. As long as they agree on the eval, they can collaborate because the eval becomes the hub. Okay, so we're searching for an eval that can work well on this problem. And what are the properties of a good eval? Is it has to be very clear, obviously. There needs to be enough headroom. So if your eval you already, like the existing models already are at 95%, probably that's not a good eval because now you're only working in the 5% zone. You want to be something that the existing model is at 20, 30, or 40%, so you have lots of space to grow. It can grow incrementally, so try to pick things that is not just, it's an aha moment and everything unlocks and that's it. It should be sufficiently diverse, so you are not solving, because you think you are solving mathematics, but you end up solving one problem in mathematics. So if you want to solve mathematics, you have to have problems in different sets, in geometry, in algebra, and so on. It has to have both difficult and hard problems, so you're not stuck not moving it at all. So you need a few easy problems so you can see some progress as you go. And obviously, it shouldn't be in the training, which is very hard these days because LLMs are absorbing every piece of data in the world. So in our case, we try to find an eval whose time of creation was after the LLM was trained. And keep a held, obviously, this is very, very clear. You have to keep a held out set that you never touch. It's not a held out set that I try from time to time. You should never look at it until you think, okay, I found the amazing solution. Now you bring out your held out set and you see. Reproducible by external teams. This is very valuable, especially if you want to publish. And if there is an existing baseline, that's really good because you know where you're starting. And again, if you want to publish, this makes publishing much, much easier. Somebody published, there is an eval, the paper was approved. So now if you improve on that number, okay, the reviewer will say, the reviewer has less wiggle room to complain about your work. Okay, so this is property of good eval. So what was the eval we picked? So again, a property that I recommend in all research projects is you pick something very small, you have some research hypothesis, you run at it very fast in a small set, and then from that small set, you can then say, okay, this is a good direction, I'm going to double down, or this is a bad direction, I'm going to go back to the drawing board. Probably this is not the domain I should be working on. Probably I need to rethink the ideas. So always think in those terms, like don't get stuck in a 2-year project where you're not validating your hypothesis. So what we did is we picked Kaggle as our eval. Everybody knows what Kaggle is. Raise hands. Okay, I will assume you know what Kaggle is. It's basically a place where there's lots of AI competitions. Very good place, by the way, to learn and like improve your coding skills and your machine learning skills. So Kaggle has a bunch of very hard competitions that are $1 million and so on. We didn't consider those because each one of those is a project unto itself. We wanted something that's more wide span and that is relatively easy so we can validate the hypothesis early on. Okay, so we picked, they have something called playground competitions. These are designed for people to start learning how to get into Kaggle. And I highly recommend them, by the way. It's a very good way to get into Kaggle, but as well to improve your machine learning skills. And so we said, okay, we're going to take Playground 3. They have generation of these. So we took the generation that was created after the LLM was trained. And I forgot how many problems it had, probably 20 problems or something like that. And what our objective is to get 85% of human performance. And we had the data on human performance because Kaggle open sources this data. Okay, so that was the goal. Now we had a very clear goal, and we can just go and attack and see what happens. We created a leaderboard. Very important as well is if you are more than one person working on a project, is you have a place where people can run there, even if you are alone, because then you can see the history, what you have done. Okay, I did this idea. You don't see here the idea descriptions, but each one has an idea, and then I ran it, and then we checked what's happening and which ideas are working best, and so on. Okay, so we have the leaderboard. Now we're ready to roll. And by the way, these things take a long time. So when you're planning your project, plan 30% of the time just to start, to set your evals, get your environment well. So then when you are doing the research, you are going fast. Everybody knows what they're doing. They have the tools. They're just focusing on research ideas. But the engineering part is always very complex and always underestimated. Okay, so first, okay, what do? You start with the most simple idea of an LLM is that we're going to do best of n. In all of these problems, we do a test and validation score. And basically the idea is you have a prompt. The LLM generates some code. This code is then is run on the validation split. This validation score can be used by the LLM to do next steps. In this one, there is no next steps. But this validation score is visible to the LLM. And in a best of 10 is the validation score that's selected. We select the top code that has the best validation score, and then we run it on the test score. So the idea is not that all the candidates are alive, is that you're using your validation to kill to kill all the candidates but one, and then you are submitting that candidate. Okay, so we're here. The humans are, this is 85% of human performance, and now we're trying to climb to get there. So if we get the LLM on base, okay, this is where we're at 50 percentile. We go next. Okay, so we notice something. The objective function is smooth. The objective function is, because on all of these problems, you are running some sort of eval and you get a number. The number is like 0.67, and you want to make it 0.99, right? So, which means, okay, it's not, when we do best of n, we're just throwing things on the canvas like this. We're not taking advantage of the curvature of the space, but we can do the most simple thing, is that we select one candidate. Actually, I mean, here it's in the picture is one candidate. We select a few candidates, then we select the best one of those, and then we say, okay, let's go from that candidate and try to improve it. So, and then we do this in a greedy search, the most simple search algorithm possible, and just with that, this is the prompts. Just with that, okay, we went from 50 to 70%. So something very easy, something very simple gives you that boost. And by the way, if you're building actual systems, always look for these low-hanging fruits that can give you a huge boost. Because if you see here, this is very simple, like it's probably 20 lines of code. And this got us 50% of where we wanted to get, right? And in some practical application, probably this is good enough. Okay, so then we say, okay, this is greedy. And as we know, the problem of greedy is that you're not exploring, you're just following the simplest path. Okay, so I want to do exploration. And okay, so now what kind of exploration do we know? Do you know what UCB is? Anybody knows what it stands for? Okay, Sami knows, but we're not going to ask you, Sami. We'll assume that you know what it is. We'll trust you. It's upper confidence bound. Okay, so upper confidence bound is a very simple formula that allows you to explore in a space that you want to navigate in, a search space typically. And it allows you to combine going for the best thing, which is the greedy search, with going for things that you haven't looked at before, which is exploration. So if you look at the formula below, you see VI is the value. So let's say I used LLM, I generated 10 pieces of code, I ran these pieces of code, and each one of them gives me a number. This is VI. Like, how good is that piece of code? And I want to select which one to use. So this is the tree search. So this is the top node in the tree search. Which one of the top nodes I want to use to explore more, to go in that direction? And so the VI is how good is the node after my test. But the greedy search would go just for VI. So now we add a component, which is, I forgot what POC stands for, is predictive upper confidence for tree search. Yeah, prediction and upper confidence for tree search. Okay, this is a constant. This CPOC is a constant that says, how much exploring do you want to do? If you want to be very explorative, you make it very high. If you want to be not explorative, you can make it. If you make it 0, you're back to greedy search. Okay, and then you have in there, the top thing is how many nodes I have, how many times I have explored all the nodes, the totality of my exploration. And then at the bottom is how many times I explored the specific node I'm looking at right now. So what is the intuition here? Is that the more you explore a node, the more this term is going to get smaller. So which means this node, you have looked at it so many times. So if you looked at it a lot, you don't want to keep trying it again. And on the top is the totality. So this is the percentage, basically, of both these things. Okay, so this and the classic algorithm, which is MCTS, uses UCB. And this is what we use for AlphaZero, for example. But in the classic algorithm, you start from the root. At every time you want to select a new node, you start from the root, use this formula, you select one node, then you go from there, you look at the children, you apply the formula, so you're applying it at every step of the way. Because in classic MCTS, you're doing, for example, gameplay. So in gameplay, you're moving in turns, and at each turn, you can't roll back. In our case, we can be anywhere. So we can look back at the nodes in any place, anywhere in the graph. So we have developed a variant of the algorithm, which we call flat UCB. And in flat UCB, it's exactly the same as MCTS, except instead of going down the tree and getting to a leaf node, we can be anywhere in the tree. So we just put them all, we apply the formula, and we select which place to explore. And the only reason it's a tree is because then we give credit not only to the child, but to all the parents as well. So the NI is going up for all the count is going up to all the parents as well. Okay, so this is actually this was probably the most innovative part of the solution we have. And then when we add that, as you see, this is a big innovation, but it gave us less than just applying this simple thing. And now we are at 75%. So, and by the way, at every one of these steps, there is not in the graph, there is 100 things people are trying, they're putting them on the leaderboard, they're not working, and so on. So I'm showing you the path of success. But in real life, you are doing a million things to get there, right? Once you know it, you can reproduce the whole thing probably in 2 weeks. Okay, so now if we look at the way we are doing the search, there's an initial code that we generate from the description of the problem. And then after that, every piece of code is generated from taking a previous code and getting the next code. So it's two different kinds of operation. It's the drafting and the mutation. So with this insight, we ran a bunch of experiments on a bunch of different models. So if you see in the drafting, the MPP is a large model and the M is a small model. On the drafting, the large model is dominant. So this is Mann-Whitney. It's just it's a very simple test that tells you which one is better than the other. You rank the results from each of the two methods, let's say the blue and the red, and then you sum the ranks. And then with that, you can see if one is better than the other. And the pink is places where it's nearly the same. OK, so the big models are very, very good at drafting, because drafting is a very complex operation. At mutating, the big models are good, probably better. The red is the big model, the blue. But the blue is the small model. But it's not that much better. It's a bit better. And but the small model is much faster. So here we have to take accuracy versus speed. And by the way, the reason for that is the small models, because they sort of go all over the place and they do stupid things, in a way they explore better. They have more diversity in their output. The big models, if you tell them the same question, they give you the same answer. So what did we do? We said, OK, let's use one for drafting and one for mutating. And OK, here we got another jump. Again, this is a very simple idea. Not very complicated, but OK, now all of a sudden you got another 10%. And so again, the intuition here is that diversity is very important. Why is diversity important? Is because you have the right to generate thousands of nodes in our case, unlike when you are asking Gemini, it has no time to generate thousands of nodes. So we generate thousands, tens of thousands of nodes, and so on. So it's OK if you have bad ones, as long as you have good ones. So what you want is a distribution with high variance, even if the median, so two distributions with one higher variance and the other one's lower variance, the higher variance will win when you sample a lot, because you are selecting the best candidate, right? So we need diversity. How do we get diversity? So one simple technique, we call it handcrafted strategies, is we just sat down, we wrote a bunch of ideas that you can use, things like, OK, play with the hyperparameters and so on. And then at every node at random, we'll select one of these strategies. And this will induce diversity, because basically you are polluting the context with something that can drive it in one direction or another. So in a sense, it's as if you had, let's say you had 10 strategies. It's as if you had 10 different models, because the model now is behaving differently. So that gives you more diversity. And you can see here the results, that without these strategies, actually, if you sample one, with no strategies, the model is superior, because the model will try to find the best strategy and then apply it. If you sample with strategies, the more samples you get, like if you go for 10 samples, then all of a sudden the strategies help you, because now you have diversity. OK, so we added diversity. And with this handcraft strategy, we got a bit. Now we are very close to the goal. We don't know what to do. We are stuck. We want to win. So basically, it's like a race. Gives you a lot of, it makes the research more interesting. And OK, now, OK, we have to cross the line. So what do we do to cross the line? So OK, can we learn the strategies from human data? And here there is a very nice innovation, is because we had the human solutions, because Kaggle actually publishes these solutions. So we can take the human solution and say, OK, because the solution is just a piece of code, we can go to the solution and say, OK, what was the strategy that was used to generate that solution? So you ask the LLM to find the strategy. And you can do this multiple steps. You can pollute the code, get the strategy. So anyways, there's a way to generate these strategies from human data. And now you have a data set of strategies. Instead of being written by a human, it is generated by AI from human data. So as we know, this is always better. And now we cross the line. OK, so this is amazing. Now we cross the line. We declare victory. So this was sort of a 3-month effort, putting like very, very focused 3 months to get there. Now, OK, we validated our hypothesis. There's something there. We actually improved the results. We have a bunch of new ideas. These new ideas could be applied somewhere. OK, so now that we cooked the meal, let's see if we can taste it. OK, so we want to taste the meal. What does that mean? Well, initially we claimed that we want to do science, but what we did is Kaggle. And Kaggle is pseudoscience. Like in a sense, the problems are scientific, but the problems we picked are the playground problems, which are more training problems and so on. So okay, now let's go to the real world. So we picked 6 science problems, and these were picked. By the way, I'm going to talk about them. I know very little, because each one of them, they have domain experts. Obviously, I don't know how to count, because I'm counting at 1. But each one of them has domain experts, and we collaborated with these domain experts who use the system to generate these, to try to solve these problems. So these are people who are really motivated, not by the computer science part, but by actually solving each of these problems. And they're ready to dedicate time, tweak things, and apply changes. So, okay, so we have, so now, if you remember in the previous thing, it was you just get the problem, and then you let the LLM go. Now we have a human. So the human is taking the problem and putting in research ideas. And then both of these things are moving forward. And then we run our system. One thing I didn't mention before is that one engineering complexity that took a lot of engineering time is putting all of this in sandboxes, because it's running on Google infrastructure and it's generated code. So we don't want generated code to be running all over the place. So there is a sandbox around every piece of code that's generated. And so now there is humans who are putting research ideas. Okay, now you can say, well, how do we know if it is the agent or the human? It's because these humans are competing with other humans who don't have the agent. So it's more like seeing if the human putting the research ideas with this machine, can they perform better than they would have otherwise? So that's the setup. And here on the side, you see where these ideas come from. So these initial research ideas could come from just a human who is thinking about it and says, okay, this is a good idea to use. Or it could be that we use an LLM to take a bunch, the human selects a bunch of paper and says, there's very good ideas in these papers, why don't you use them? Or it could be prior ideas. So in many cases, the engine created ideas, and then there is a human that said, oh, this is a good idea. And then from another run, that was a good idea. So the human would say, take idea 75 and idea 26, put them together and try again, right? So this is the recombine. And finally, we use Gemini as well. So there's no human in the loop. We tell it, okay, do Gemini, deep thinking in Gemini and do Gemini research. Okay, so now on a bunch of problems, if we see single sample, of course, we want to compare, because as well, we are generating lots of samples. So it's not fair to compare with just a simple LLM. What you want to compare with an LLM that's running for thousands of times, so we do best of 1,000. AID is a public algorithm that was, at the time, sort of state of the art. And now we have tree search. So our algorithm without a human reaches here like probably 65%, something like that. Now, once you add a human, you can go better. And there's a specific technique with boosted decision trees as well that got even better, and I can talk about it later. Okay, so we see, okay, it's good, and very quickly, I'm going to, how much time do we have for questions? How much, 15 left? Okay, so I'll try to go in 5 and leave 10 minutes. Okay, very quickly. Genomics, so there's a problem. So the only reason I'm showing this is to show the variety of problems. I'm not trying to explain the science behind these things because, as I said, I don't know them very well. So batch integration, single cell RNA sequencing, it seems to be a huge problem for biologists. And basically what it is that if a biologist is getting data from different batches, so different labs are sending it different data sets, and now you want to put them together to create a very large data set. What happens is that there is patterns that come because these labs have different settings. Could be the temperature in which the thing is done, or the strain of RNA in which they ran the experiments, and so on. So what you want is to get this thing out so that the data you have is independent of the lab, so you can have one big data set that the only patterns in there are the patterns you care about, not the patterns specific to the experimental setting. Okay, so this very big problem. There's huge competitions on this. And here you see like different techniques, and the blue bars are the bars done by our systems, and the reds are the base methods, and then there's difference with the human, without human, and so on. Okay, the second one is predicting COVID-19 hospitalization. We have data from every single zip code in the States, or something along these lines. And what you want to do is, if I give you what happened in month 1, can you predict day by day, zip zone by zip zone, what's happening in month 2, right? Very complex. So here again, here lower is better. So we see the base methods are at the red, and our methods are doing really well. This is segmentation for remote sensing. Again, so it's an image. It's a very different kind of problem. It's image. And again, it's generating an algorithm that will generate a model that will do this. So now it's doing sort of machine learning research. And it gets MIOU is, I is intersection, mean, intersection over union. Okay, so this is the number that we are measuring is of the union of the segmentation and the real segmentation, and then you see the percentage that you are shifting. Okay, this is really cool. This is zebrafish, which are very beautiful fish, and what they have done is that they have found a way to get their brain activities on brain region level, and they film them over hours with different visual stimuli, and this will affect their brain behavior. So now there's a bunch of experiments you can do. Like I give you the brain state. Can you guess what the stimuli was? So sort of like reading the brain of the zebrafish. Or I give you what the zebra is saying and probably the state, and can you roll the state over time? So again, very good results. Here it took some human intervention, human recombined a bunch of ideas, but as well, they beat the state of the art with these techniques. This one is purely mathematics. So doing integrals, the standard method is Gaussian quadratures, which I don't know how it works, but basically there is a famous library called Quad, and people use it to do integrals. And but it fails in certain class of integrals. So we had a training set and then a test set of 19 integrals that mathematicians have found where it fails. And our method solved 17 of them, while Quad fails all of them. So this was a good result. Time series prediction. This is GIFT eval is just a data set of data sets of time series predictions. So it's a very well-known time series sort of competition. And here they got very good results. Okay, what are the lessons learned? Is think hard about the problem to solve, because you think you might be doing a month, but it ends up being 2 years. Pick evals. I think evals are so important. It's very important to pick the right eval. And start with a simpler eval, iterate on it until you validate your ideas, and then move to the bigger one. Obviously, leaderboards are important. And the idea is you are not searching for one thing. You have a team of people, they're all coming up with ideas, and typically is the combination that makes it work. Except in some amazing cases where there is one transformative idea. But in most of research today, it's a combination of things that are improving on the results. And that's the advantage of the leaderboard, is that you can see, okay, there's this cool thing happening here and this cool thing happening there. So at the end, what you see our papers, there's so many names, is because each person came up with an idea and all of these ideas were put together. And collaborate with domain experts. The other thing is very important, is don't just dive and hide and come back in a year. Like you come back with an amazing result. Actually stop at milestones, and even if the results are incremental, document them, validate them, create some artifact that you can share with the community, and whether you share it outside or just inside. I think it's very important to keep you on a clean basis, because if you go deep, you might get lost. And at the end, you might not even be able to reproduce what you were doing before. And that's it. Excellent.
I have a question there. Thank you, Mourad, for the great talk. Just out of curiosity, if you were to use a genetic optimization algorithm like AlphaEvolve,
yes,
how well would it perform, like for the
yes.
Kaggle competitions?
Yeah, this is a very good question. So I think that research and evolution are two families of problems. And in a sense, they could be, there's places where they can morph to each other. So if you change like there's a set of parameters where tree search becomes evolution and a set of parameters where evolution becomes tree search. But the language of the different algorithms and the sort of the history of this algorithm give you different tool sets. So AlphaEvolve when we did this work, AlphaEvolve already existed, and we tried it on some problem, but we said, let's try something else. And hopefully these ideas can be merged together to make something even better. AlphaEvolve is very, very, very good at searching in a space where it's sort of a needle in a haystack kind of search. So you want to find something that is very, very, very hidden. So your exploration should be at a very high level, and you need to use a lot of compute. These methods are probably in the middle, because the tree search algorithm you can tweak the C parameter, and so you might be more sample efficient in the beginning. While AlphaEvolve, I suspect, and I think it's very hard we haven't done a benchmark to compare them. I suspect AlphaEvolve would be better at problems where the solution is very, very well hidden. So like the neighborhood of the solution doesn't have indication that this is a solution. You cannot just get there by zooming in. Thank you.
Good morning.
Good morning.
You talked about deciding how to measure the problem and evaluating it is a very big part of the research. So if you have a problem that's some kind of human related, it's really hard to have one metric to measure it. How would you approach this, and what are the methods to use?
Yeah, I mean, obviously it depends on the problem, but a technique that's, in many problems you can say, okay, I have this method. Ideally, I want it to be on a human. I want to test it on a human, but human testing is very long. So can I build a simulator of the human? And this simulator is frozen, so it's not polluted by the training. And I think LLM give us this capacity now, which we didn't have 5 years ago. So I think with LLM, you can build the simulator while being very, very careful, because you know that the simulator is not the human. But if your method is, if you think that your method is general enough that should work on the human and the simulator, you can test it on the simulator, because then you can iterate very, very fast. But you have to be careful to stop at some time and to go back and test it on the human. Yeah. Now, testing on the human, if you want to run real human experiments, is very complex and require ethical approvals and these kind of things. But in many cases where we have, because I'm working on projects where lots of humans are involved, what we do is the team becomes the testers. So we do early validation with the team just to make sure that, okay, when we go to actual humans, which is very expensive and time consuming, we're going with the best results possible.
Thank you so much.
Thank you.
I do actually have a question. So yesterday's talk on the thinking for LLMs, they do spend a lot of time doing exploration and thinking during the talk and pre-training. In here, you are also doing some sort of exploration post-mortem. What's the intuition in why don't we believe the LLM actually did this exploration during the pre-training? What's the benefit of doing the pre-generation at this point? And how does this differ from doing planned approach? So you ask the LLM to plan its horizon beforehand and then exploring the planned tokens rather than actually doing the drafting at every next stage.
Yeah,
so two questions.
Yeah, I think this is a very good question. So, and we are exploring ideas in that space. The specific difference between what typically people are doing in thinking and what we are doing is that typically, and not always, but typically in thinking, the question is hermetic. What I mean is that you can think about the question without going to the outside world. And typically, in thinking, you are looking at 500 to 1,000 language calls. While here, we're thinking, and you're not doing a lot of parallelization. You do a bit, but not that much. While here, these are for problems that are very valuable in a sense. And as well, the specific thing is that these problems, you can actually run experiments and get results. So, I mean, obviously in thinking, you can add tools, and these tools can run experiments and so on. But in the most canonical way of doing thinking, you are not doing that. So here we focus, you can think of it as a subcategory of thinking where you need to run lots of experiments, and you can afford to run on thousands of computers. So it's in that zone, then now we're thinking, what is the best algorithm? And we're exploring now, so here we have an algorithm that's doing it. So what we're exploring next steps is to say, okay, can we replace the algorithm with the LLM? Which now becomes very close to the thinking technique. So probably the two things are merging over time.
Thank you so much. Any more questions, I think? Then I will ask one final. Yeah, one.
So thank you very much for your interesting presentation. I have only one question. So we saw that the proposed framework outperforms the codes available in the internet. So how to be sure that the solution proposed always innovative solution, as LLMs tend to search and copy and paste sometimes the solution available in the internet. So.
Yeah, actually, we think that most of the time it's not innovative. But what these models are very good at is doing the hard work of finding ideas that are not innovative but out there, but putting them together in the best possible ways. So because obviously humans, we are limited by our time and our patience, but let's say there's 50 good ideas in this room to solve a problem, and now you want to get the best solution that probably combines them. Now obviously the combinatorics is so large that you can do it just by brute force search, and putting humans to try multiple variations is very costly, and I think this is where the sweet spot that the LLM can do. So I think these models would be very good at squeezing more value from existing ideas, as well as coming up with new ideas. But we're not claiming that they're coming up with very novel solutions, but we're claiming that their results are very good.
So my question is actually related to, let's say, self-improving large language models. And basically the question is scale the only problem that we have when considering self-improving large language models? And is that an avenue? Thank you.
Yeah, so no, I think it's much more than scale, because self-improvement requires as well, I mean, there's lots of open scientific questions about self-improvement. There's two ways to think about self-improvement, is that if self-improvement is, okay, whenever there is new data, I train on it, then this is scale. But I think there is more to self-improvement, because there's ways to do self-improvement that don't require data. For example, you do your own experiments, right, as an LLM, and from your experiments you can learn a few things. This applies a lot to, let's say, computer science and areas like that you can run experiments externally. There's as well active learning, where the LLM will seek information. So these areas, I think, are not scale problems. There is lots of discovery to be done in that space. In our case, we're very interested in thinking about self-improvement, but not solving self-improvement in the general, more self-improvement for our algorithm. So what we would love to have is that every time you give me a problem, because we're spending so much compute to solve it, is can we learn from that so that the next time you give me a problem, I use 90% of that compute, and so on, and then I can push the frontier better. So that kind of self-improvement we are very interested in. Thank you. Okay, thank you very much, and good luck with the rest of MENA.